So not much on this quiz. Means you should really be angling to get high as possible. I sent out this message over the holiday. Noticed that from exam 4, that's only from 2022, but exam 3 is those questions from 2018 to 2021. So most of the stuff is from exam 3, but make sure you don't neglect those questions from exam 4. But that's only what, 6, 12, 20, 25, 32 questions. It's only 32 questions. So maybe I'll just focus on those for now. We'll need to focus on other things for the exam, but for now, let's just focus on those things. And then those questions, they'll be about the nature of light, about the electromagnetic spectrum, a reflection. You'll probably have one of these on there. And then probably 4 or 5 of the questions, most of the questions come from refraction. So like you'll have questions that are like these: organizing the electromagnetic spectrum. I want you to know the nature, the history on the nature of light. This one of these reflection problems, but most of your stuff is going to be about refraction, which also includes total internal reflection. Okay? Are there particular questions that you want to look at?
We do 16 on 21.
Yeah, that's exam 3 on spring 21. Okay, well, you're definitely, like this one right here, you're definitely going to have one like this. It might not be this one, but if you notice, there's one like this on every exam, and you'll have one of these on your quiz. They're not hard. You just need to remember that this is a perpendicular angle, so that the sum of those two angles, the 40, and then the other angle is equal to 90. And then you also need to remember that for any triangle, the total of all the angles is 180 degrees. So here, the light ray comes in and it's reflected by the law of reflection such that this angle is equal to the incident angle, so that's 40 degrees. That means that this angle right here, well, is 90 minus 40, or 50 degrees. And then notice that I have 50 and 90 already, so that's 140. That means that this angle has to be 40 degrees, which means this angle is 50 degrees, which means that the reflected angle is also 50 degrees. Okay? Be careful though, notice that I have other options here, like I have 40 degrees, that was an angle that came up commonly. I also have 90 degrees there, I have 140 degrees, like all of those angles were angles that came up at various points in determining what is the reflected angle. So just because you see a number that's in the options doesn't mean that it's the answer, of course. Okay, I think y'all know that from my test. The only difference sometimes here, this triangle was an equilateral or was a right triangle, but that doesn't always have to be the case. In fact, sometimes, often, this angle for the two mirrors is not 90 degrees. It's something more or less than 90 degrees. Okay? Definitely have one like that. What else? Number spring 2026. Yeah, the index of air is always 1. This one right here? Number 26? Okay. Okay. On these, it's really useful if you draw a picture. If there's no picture, I would definitely draw a picture. And so here, light is traveling from glass to air. So I like to draw it here. I have glass on this side. I have air on this side. So my light is coming in like this. So the angle that is over here, this is my incident angle. It's the angle, the first angle that you have, because the light ray is incident upon the interface. That is my incident angle. Also remember that when I have total internal reflection, that always occurs when I'm moving from a high to a low index. Let me write that down. So TIR, total internal reflection, occurs when I'm moving from high N to low N. It does not occur if I'm moving from low N to high N. In fact, in this situation, if you try to calculate the critical angle for your incident angle, you're going to get an error in your calculator. It's just not possible. The light just doesn't bend in that way. And the reason is this, that when I'm moving from glass to air, think about my wave fronts here. It's going to be moving fast on this side, slow on this side. So the light ray is going to bend away from the normal, which is what you need in order to get total internal reflection, because you want that light ray to not leave the medium from which it's coming, to not leave the glass. So total internal reflection occurs from going from high index to low index. I always remember that because, you go to the store and you see those little things with all the little fibers coming out that have the little tips of light on them. Those fibers are made out of plastic, which has a fairly high index of refraction. And they're surrounded by air, which has a low index of refraction, which is why you're able to capture that light inside of those little fibers, the little plastic fibers. So I'm moving from high to low, which in this case I am moving from a high index to a low index. This is N equal to 1.5. Somebody said here N is equal to 1. This should be low, not 10. The index for air is always 1. I don't give you that. I guess if you ask me that, I might tell the class, but I just want you to know the index of air is 1. Okay? Index of air, what is it? 1, right. It's the same as a vacuum. Actually, like we said in class, the index of air is actually a little bit higher than a vacuum, but not much. It's like 5 decimal places out. So here, I would set up my lens equation, or my law of refraction. N1 sine theta 1 is equal to N2 sine theta 2. That's going to be 1.5 sine of theta 1. That is my incident angle, is equal to 1 times sine of 90. Remember, that refracted angle and total internal reflection is always going to be 90 degrees. And then I would solve this.
How is it 90?
So for total internal reflection, in order to find the angle at which it occurs, that light ray has to go along the medium. It's like it doesn't escape from the medium. And so this angle right here is 90 degrees. Of course, that's the minimum incident angle. If you make this angle bigger, if you move this up like this, then this thing isn't going to go at 90 degrees. It's going to reflect back down upon itself. Okay, but if I'm looking for that critical angle, I set theta equal to 90. Okay? And then I don't know what the answer was. Do y'all know what it is? 42. Yeah, so if I solve this for theta, I get theta 1 is the inverse sine of 1 divided by 1.5, which is equal to 42 degrees. Thank you, Wayne. Okay? Is that good? Those are probably the more complex. Don't forget that if I get an error in my calculator, it's because total internal reflection doesn't occur because I'm trying to move from a low to a high index. And draw a picture. It really helps to draw a picture. Otherwise, you're going to get your two media confused. I'm moving from what to what, and where is the index of refraction? Draw a picture like I've done. It will really help you to keep everything straight in your head. Joey?
And it's going to turn in the direction of the lower end, right?
If it's moving from high to low, it moves away from the normal. If it moves from low to high, like if it's moving from a low index to a high index, like this, it's going to bend towards the normal. And since it's bending towards the normal, I can't get total internal reflection because it doesn't come back into the medium. Remember, we can do the wave fronts here. When it gets to this point, because it's moving to a high index of refraction, that means it's moving more slowly there. And it's moving fast over here. So this wavefront comes around and gives me my ray moving towards the normal. Okay? You're going to have some like 24 here as well. Let's just do this while we're here. Some ranking problems. You'll definitely have one of these. There's one in every test, so go back and look at them. Here I want to rank them from the highest to the lowest index of refraction. So first, just look at medium 1 and 2, then look at medium 2 and 3, and then think about medium 1 and 3 and how those are related to one another. So here, it's traveling along. At this point, it has to move faster. That means it's moving slow up here. That means that the index for medium 2 is smaller than the index for medium 1. So N2 is less than N1. I'm ranking them from highest to lowest. So any that show N2 bigger than N1 are going to be wrong. So B and D I can get rid of because it shows that 2 is actually bigger than 1. Yeah, Joey.
And how do you know it's fast at that point that you just showed?
Ah, okay. So I know that it's fast because of the way that it bends. So if it's going faster here, it's going to bend in this direction. Remember the twin propeller boat or the bulldozer or the tank? If I want to go in this direction, I need to make this side go faster. If I want to go in this direction, I have to make this side go faster. And so that's what's happening here. In order to go in this direction, this side has to spin faster to go in that direction, just like a tank or a bulldozer. So I know then that it's traveling faster or slower. Now over here it's a little bit different. I'm moving in this direction. That means I must be traveling faster here and slower here. So that means that N2 is, what is it, bigger or smaller than N3? Smaller. N2 must be smaller than N3. So let's see, I'm going from highest to lowest. So any that show 3 smaller than 2. Yeah, so now I'm down to these two. So C or E. Yeah. All right. So now in order to pick between those, I have to look at medium 1 and medium 3. I like to draw them separately because usually by now my figure's all messed up like it is now. So I'll draw medium 1, it's right here, and then medium 3, notice that it bends towards the normal like that. And now I can just imagine that medium 2 isn't even there. So I can draw my wave fronts. It means it must be traveling fast here and slow here. That means I have a small n and a big N. Our N1 is less than N3. That means that this one is not the answer. So C must be the right answer. That's right, isn't it? Did I do it all right? 24C. Yeah. I like these. They're kind of difficult to do. Like you got a lot to think through, but ranking problems are really common on standardized tests. So I want you to have some experience with ranking problems. I'm not saying you're going to see this question on a standardized test, but just ranking problems, the process of going through them is a good thing to practice for your MCAT or your GRE or whatever it is that you're taking for your various professional schools. All right? Practice those, okay? Practice them. You can memorize them, but it's probably better for you to just memorize the process. That way you'll be ready for the exam too. Yeah, those are hard too. Oh, I thought it was going to be an easy quiz. I think this is probably the easier quiz. Don't y'all agree? This is the easier of the quizzes that we've had? Yeah.
23, we're looking for it's always the higher index.
Yeah, the one that's bent most is the higher index. Yeah, so a bigger N means that it's going to bend light more. Okay, so here there are two things I want you to know. I want you to know that if N is big, it bends more. And then I also want you to know the colors, that this is blue light and this is red light. I should do it. Blue at 400, the short wavelength, and then red light is the long wavelength. I want you to know how the colors are associated with the wavelengths. And so here the color that is bent most is the color at 400 nanometers, which is the blue light.
Because the N's higher right there, right?
Yeah, N is at 1.53 here instead of 1.51. Other questions, John? Sort of skimmed through them. You see a lot of these are similar. You'll probably have one like 22. That's just where you're calculating the refracted or the index of refraction or the angle of refraction or one of those. What are you going to do?
That's that N1 sine theta.
Right. You're going to draw a picture. Please draw a picture. It will help you. If you just do it in your calculator, you're not certainly going to get it wrong, but you're much more likely to get it wrong. Draw a picture. It will really help you when you're doing this. So here I have a light ray is incident on air to glass boundary and is refracted in the glass. So what it's telling me there is I'm starting in air and I'm going to glass. I can tell that because the light ray is in air and then it's incident. And it tells me that angle is 30 degrees. And then as it moves into the glass, it tells me that the angle is 21 degrees, which jives with what I think it should do, right? If I think about my wavefronts, it's going to slow down here and go fast here. So it's going to sort of go around. And then I would use that to find my index of refraction for glass. So N for air is 1, sine of 30 equals N sine of 21. I solve that for N. You'll have all of these different types of questions because there's not that many. Make sure you know your electromagnetic spectrum, high to low energy, gamma, all the way down to radio waves. Gamma rays have a really short wavelength and a really high frequency. Radio waves have a really big wavelength and a really small frequency. Yeah. Okay. Other questions, Joe?
I know we kind of just like literally went over this, but can you do 21?
Yeah, on the same exam.
Yeah, right above 22.
Yeah, of course. So you might have one like this too. This one's simpler than the one that we just did, but still a possible question. So I want to know, what about the indices of refraction? Just remember, big N, that means it goes slow. Small n, that means light travels fast. Okay? So it depends the relative size of the index of refraction. Draw my wavefronts. In order to move in the direction that it's going, I need to travel fast in this medium while it's going slower in this medium. So N2 is faster than N1. That means that N2 is less than N1. It's faster, so that means that the index of refraction is smaller.
And let's say it was like opposite. Let's say it was fast on top, slow at the bottom. That would be N1's greater than N2.
Well, that would be a different situation. It would look like this, right? Where I would have the light come in. It has to travel slow here, fast here, in order to bend around and follow a path that's like this. So that means if this is N2 and this is N1, N2 is bigger than N1. Don't try to memorize it. I always try to just go through that process, because what the process isn't that complicated, and if you get that, then it'll apply to a lot of different situations. Instead of just memorizing, oh, if it does this, it's less than. If it does that, it's more than. And you flip the figure around, and then you forget how you apply it. Just remember that if it travels faster, that's going to bend away from the normal. If it's traveling slower, it bends towards the normal. Okay? What else? 18? 23 and 24? Yeah, so this is a total internal reflection. Now let's think back. So the total internal reflection, the core, which is where the light is trapped, it doesn't come out of it, it's like the fiber optic. Is that a high index or low index material? It's a high index. Think those little fibers coming out, right? The plastic fibers have a much higher index than the air that's around them. So the one of these that will serve as the cladding, and in a fiber optic, the cladding covers the core. So you have your core, and then you have this protective coating over it. You don't have to have that, but in this case, just to protect the fiber optic, they put this cladding around it. And so if I have flint glass and crown glass, the one that I want to have in the core is the flint glass. This is going to be my core. And then I'm going to have the lower index, the crown glass, as the cladding. Okay, I have the low index material as the outer part, which is the cladding. Why is that? Oh, so if I imagine my light ray coming in here, I have n equal 1.66 and n equal 1.52. This is the inside of the core. This is the cladding. I want it to be such that when this refracts, it doesn't refract into the cladding. So if I imagine my light rays coming in, I want this ray to refract so that it's bent along that interface. But if the indices of refraction were different, if they were switched, so that I had 1.52 in the core and 1.66 in the cladding, it wouldn't bend away from the normal. Instead, it would bend towards the normal. And if it bends towards the normal, you're never going to get total internal reflection because it's just bending the wrong way. You want it to bend so that it comes back into the core. And if I switch these two, it's not going to bend that way. It's going to bend towards the normal instead of away from the normal. For total internal reflection, I have to move from high index to low index. Otherwise, you're never going to get total internal reflection. It's just going to, well, if you try to put in your calculator and get an error, it physically would not work. Now, in this next one, you had to actually calculate the critical angle. If you remember, the critical angle is the first angle at which you get total internal reflection. N1 sine theta C is equal to N2 sine theta 2. Where here, theta 2 is just equal to 90 degrees. That's our first occurrence of total internal reflection. And then I solved that for theta C. So what was it, 1.52 and 1.66. So this would be 1.66 sine of theta C equals 1.52. Sine of 90 is just equal to 1. So theta C is the inverse sine of 1.52 over 1.66. Do you know what the answer is? It's B, so it's 66 degrees. The sine of what? Yeah, theta 2 for total internal reflection will always be 90. It's a special case, really, just a special case for the law of refraction where theta 2 is equal to 90. Because when theta 2 is equal to 90, that means that that light ray is not leaving the medium. When my angle over here is 90 degrees, like it is here, this ray is still in the core. It hasn't gone into the outer medium. It's reflected back on itself, back into the core. And that's what you want. You want those light rays to stay in the core. For fiber optics, if that's what you're trying to do, that you're transmitting information by light instead of transmitting it by an electrical signal. With most of our data is now transferred in that way, it's much faster. Okay? What else? At all? String of 21. A lot of them are sort of repeats of one another. They're just slightly different. Which one? Yeah. I would say here, first of all, I check, can I get total internal reflection? Can I? Yeah, because I'm moving from a high index to a low index, so I can get total internal reflection. Um, so then I say 1.4 sine of theta 1 equals 1 sine of 90, and I solve that for theta 1. If you get an error, go back and look and make sure, am I moving from high to low? If you get an error in your calculator, either you put it in there wrong, or maybe you are moving actually from low to high index, in which case your calculator's right. You can't have total internal reflection. All right, y'all? Good? All right. I want a good showing on this quiz, okay? Remember, I will drop your lowest quiz grade, so if you made all perfect scores, you don't need to take the quiz, but I really encourage you.